Section 10.2, Connecting Transformations and Symmetry. The goal here, we're going to determine if an object has reflection symmetry, rotation symmetry, D-type symmetry, and or Z-type. Sounds like a lot, but really what we're going to be focusing on mostly is reflection symmetry, rotation symmetry. If it has both double symmetry, so to speak, you'll be looking at D-type symmetry. Double type would be one way to think about that, as both. The Z-type symmetry is just symmetry that has rotation symmetry. And you'll see there's going to be a subscript that goes with the D and the Z-type that tells you how many rotations there are, maybe how many reflections there are. So really we're just looking at two types in a sense, and then there's classifications based on which ones you have. Symmetry overall is going to be defined based on the concept of, following from rigid motions. So your rigid motion of reflection, your rigid motion of rotation, those are what's coming in here. But symmetry is when the object is a rigid motion that moves an object back onto itself. So if you're reflecting, then it looks like when you're done reflecting that you didn't reflect anything. It's like, oh, it's back to where it started. Same thing with rotation symmetry. You'll rotate it and it looks the same as when you started, even though maybe it has turned a little bit. Depending on the shape, it could look just like where it started. So symmetry, just when it looks like when you started. So the symmetries that we'll consider are reflection symmetry. It occurs when an object has a line of symmetry going through the center of the object, and you can fold the object on this line, and the two halves will match. An object may have no reflection symmetry or have one or more. So if you look at a piece of paper, if you fold it in half the long way, the halves would match. Each half would match. If you fold it across a diagonal, those halves, when you fold it up, aren't going to match. You'll have one corner popping out over to the left or right of the other corner. So the diagonal wouldn't be a line of symmetry, a line of reflection symmetry, but the line down the middle would. And then if you fold it in half across the long, or I should say, so it folds and has the shorter half, so to speak, basically that would still be another line of reflection symmetry. So there's two lines of reflection symmetry on a piece of paper, folding it down the middle and folding it across the middle. But the diagonals don't work, so you only have the two, middles from the top and the side. So another example here, looking at a triangle, and I'm going to pretend that this triangle is an equilateral triangle. All three sides are the same length. And actually, I'm going to go ahead and not pretend. I'm going to grab a shape that's an equilateral triangle. So now there will be no argument as to whether or not all sides are the same length. So from here then, if you start looking at this, you got one line of reflection symmetry right down through the middle. Fold that in half, there's going to be the two sides matching up perfectly. You have another line of reflection symmetry going through here. Not all triangles are going to have this one because not all triangles are equilateral. And then you would have another one coming through, and that's terrible. Let me try and redraw that. Sometimes it's hard to draw on a screen. So you'd have another one there, and move that down just a little bit. So in this case, you have three lines of symmetry. You got 1, 2, 3. A common mistake is that people will go around and double count these things here, here, and here. Those aren't extra lines of symmetry. It's just the other side of the line. So yeah, that's why I drew it in different colors. So you could see there was just 3 different lines, not 6. So just be careful with that. So you got 3 lines of symmetry for this particular shape, the equilateral triangle. for rotation symmetry, basically that occurs when an object has a rotocenter in the center of the object, and the object can be rotated about the rotocenter some degree less than or equal to 360 degrees, and is a match to the original object. Car rims, rotational symmetry all over the place with car rims. It can roll maybe 60 degrees or something, and it looks the same as what you started with. If you got a 6-spoke wheel, then you'd be able to rotate it 60 degrees, and it's like, oh, did the tire move? And maybe you got to look at the wording on the tire, and you're like, oh yeah, it moved. But just judging by the rim, you might not be able to tell it moved. So that would be one of the rotation symmetries of a 6-spoked wheel. So every object has one or more rotation symmetries because of this equal to 360 degrees being allowed. That means you can spin all the way around and get back to where you started, and it counts. So humans, if you were to stand with your arms out, your legs out, and like stand like you're doing a jumping jack or something in mid jumping jack form, and then if you were to like spin around your belly button or something, like center your body, basically you're going to go 360 degrees before you come back and look like where you started. So humans have, in that standing, have a single rotation symmetry. Now the triangle, the equilateral triangle again, this one would have 3 rotation symmetries. And why? Well, this corner up here, if we rotate it this much and get down to here, it's going to look the same because it's equilateral triangle. We could rotate that top over to here and it'd look like we hadn't moved it. Or we could rotate it all the way around and it wouldn't look like we moved it. So there's 3 rotation symmetries. And how do you figure out the degrees of the rotational symmetries? Because basically what they're going to be asking in the homework is to list the rotation symmetries with degrees. So noticing that you have 3 rotation symmetries and knowing that there's 360 degrees total, you just divide 360 degrees by how many rotation symmetries there are. Then you get 120 degrees. 120 degrees is the first rotation symmetry. So you start that out. And then you add that number to itself. So 120 plus 120 gives you 240. And then you add 120 to that number and you get 360. With all of these, you should always reach a point where you're getting to 360 and that's where you stop. So these would be your 3 rotation symmetries. You may be noticing that there were 3 lines of symmetry on the equilateral triangle and 3 rotation symmetries. Let's see if that's a trend. So D-type symmetry. Objects that have both reflection symmetries and rotation symmetries are type D sub n, where n is either the number of reflection symmetries or the number of rotation symmetries. And basically, it's if an object has both reflection and rotation, it is always the same number n of each kind. So what I like with these is when I'm thinking about the rotation, it's like, okay, I know if it's got reflection, it's got to match the rotation. So that helps me kind of make sure, kind of as a check. Now, if you don't have reflection symmetry, then you just got to, basically focus on the rotation, and it should only have one. Like if there's no line of symmetry at all, then there will be one rotational that comes around. But if it doesn't have that reflection, it wouldn't be a type D. So if it has both, then it's going to be a type D. If it doesn't have both, this is the key word there, it will only have rotation, and it will only have one rotation, 360 degrees. So just kind of keep that in mind. So for example, this equilateral triangle that I've been working with, this thing has a type D3. It had both reflection and rotation, so it's a D type, a double type, and there were 3, so D3. The Z type is where there is no reflection symmetry, only rotation symmetries, and it will be type Z sub n, where n is the number of rotation symmetries. So there are shapes in a setup above there, mostly it's going to be rotation is 1, at least 1, if there's no reflection. There are some shapes out there that do have more than one rotation and no reflection. So it won't have both. And one shape, and let me see if I can actually get this up here in a nicer, might be able to do it with this. Let's see. That's forcing me to do a square. All right, let me try this one real quick. And if it doesn't let me do what I want to do, nope, it doesn't. All right. So trying to get some fancy shapes in there to avoid drawing, but let's just go back to drawing. You'll have to live with this crummy drawing. So you got a parallelogram. So pretend it's a parallelogram where the opposite sides are parallel. There's no reflection symmetry here. You can't go across here, fold it in half, and have it line up. That's not going to happen. You can't do this because you fold it and it's going to look something like that. Or you fold it over, it's going to do something like that, something weird. That's not going to work. So this one has no reflection symmetry. So it's not a type D at all. As soon as you see no reflection symmetries, no type D. But with the rotation always at least being 360, you're going to have a type Z. And in this case, if you were to rotate this 180 degrees, actually, you get back to a shape that looks like where you started. So parallelograms actually have 2 rotation symmetries, 180 degrees and 360 degrees. So this would be a type Z2, Z sub 2. A lot of times when there's no reflection, it's just going to be a type Z1, but certain shapes like a parallelogram, and there's some others out there, maybe they got a little bit more, would be a higher subscript for the Z. All right, let's do just a couple examples here. I just pulled a couple of pictures. These are going to be similar to like what you see in the homework and whatnot. They're going to give you some shapes, and you're going to have to draw lines of symmetry. So in this first one, the line of symmetry that I'm seeing, there's only one, would be right here through the middle. This isn't going to work, this isn't going to work, this isn't going to work. None of those are really going to give you a folding. Oops. Let's go back over here. None of those are going to give you a folding thing, and I guess I can't do that, where you end up with the match. So I'm trying to delete this, but it's being very crazy for me today. So there's only the one line of reflection symmetry, and that would be one rotation symmetry. You've got to spin this thing 360 degrees. So if there is reflection, you're going to see that rotation will always match it. So one rotational. So we would say here, this is a type D1. Since it did have reflection, it's a double type. And that's basically going to be it. You're going to see some different shapes, and you'll just have to think about it. If you have questions, please ask.